In this follow along, we're going to look at the Horner-Wadsworth-Emmons reaction, which is related to the Wittig, but has some advantages that we didn't see in the Wittig reaction. So let's go over some of those advantages. We're going to use a more reactive phosphonium ylide. The advantage to this is that we are going to see this ylide react with aldehydes and ketones. So yay, we can react it with ketones a little bit more readily now. The second advantage is that instead of creating this triphenylphosphine oxide, which I don't know if you've remembered me saying, but the byproduct triphenylphosphine oxide is actually really difficult and annoying to get rid of. Just when you think you've triturated all of that solid byproduct out, you think, great, I've got all this white solid, that's the triphenylphosphine oxide, you filter it away, you take an NMR and you still see those darn phenyl rings in the aromatic region, and you're like, gosh, I guess I still have some more byproduct in there. It's actually quite difficult to get rid of all of the triphenylphosphine oxide. It tends to stick on columns and streak, and it's very difficult to separate out. So one of the benefits to this reaction is that you end up getting a water-soluble phosphate ester as your byproduct instead. So with simple extraction techniques, your compound hopefully goes into the organic layer, and this water-soluble phosphate ester goes into the water layer. And through extraction processes, you can easily separate out the byproduct. So that's a great advantage. Thirdly, the reaction conditions are available to achieve both E and Z geometry. So we saw that in the Wittig reaction as well. So understand that I'm going to give you a very general mechanism for this particular olefination, and then understand that you can go into the literature and find conditions to favor your E double bond or your Z double bond. So how does this work? Well, we have to start with some very stabilized ylide, shown here. We could purchase it. It's kind of pricey, but you can also make it. Making it is its own named reaction called the Arbuzov reaction. So you purchase this phosphonium species and you find an ester with a leaving group at the alpha position, and when you react them together, they undergo an SN2 reaction. And you're at this intermediate salt, which then undergoes a second SN2 reaction where the Br- attacks this carbon, giving the electrons to the oxygen. Or you could write it as I did in the product, as instead of as the charged ylide, you can write it as its resonance with the pi system. So that's the Arbuzov reaction, and that's how you make this very special reagent to undergo the HWE, as some will write it. Very commonly written HWE reaction. So how does this work? Well, you're typically going to be using some basic conditions, and as you can see from down here, you can control this reaction through the types of bases that you use and also the counterions that you use. So the metal counterion, sodium or lithium, and the type of base you use, sodium hydride or some weaker base like DBU, these are amine bases, much weaker. You can do any of those. And so there's some leeway there. But either way, you need a base and you need a metal counterion. So the hydride is going to go after the most acidic proton, which is the one that's alpha to both dipoles. And you could understand that you form an enolate, or you could write it as the negative charge at that alpha position. That negative charge is what's going to react with our carbonyl, our aldehyde or our ketone. The O- of our ketone interacts with the phosphorus in that four-membered ring transition state that we're used to seeing. And then that collapses just like a Wittig to give you your new double bond. So here's the new double bond. If I were to number the atoms, you could say this is carbon 1, and the carbon 2 is the alpha carbon, and we lose that phosphonate salt, that phosphate ester salt, in the water layer. And these are generated in pretty good yields. They're generally going to give you an E alkene, which is trans, even when doing an intramolecular Horner-Wadsworth-Emmons. As long as your ring is large enough to support a trans double bond in it, understand that a six-membered ring can never have a double bond that's trans. It's always got to be cis. But once you get to eight-membered rings, trans double bonds in the ring become possible. And so even when you have larger rings and you use this reaction, you can afford a trans double bond. Now, how does this work? Well, I'm just going to give you a very brief overview of this. If I color code my systems where my carbonyl is in yellow and the phosphonium species is in blue, okay, when those interact, you can see I have the enolate written of the ylide. The metal, in this case, will be the sodium or the lithium. Now, lithium is often used because it has its chelating properties. That helps chelate this system. And what you'll notice is that originally the lithium is chelating the phosphorus oxygen and the enolate oxygen. And then very quickly, under a fast equilibrium, it swaps out for being chelated with the aldehyde or ketone carbonyl oxygen. So you can see now the lithium is chelating two different oxygens, preferentially the ester oxygen and the aldehyde oxygen. Now, when this original system sets up, there is some steric hindrance between your R group and these ethoxy groups off of the phosphorus. The alternative would have been for the aldehyde to have the hydrogen on this side and the R group on the other side. But the reason why I drew it this way, despite that steric hindrance, is because the first step is fast. Even if the hydrogen was, even if I flipped my aldehyde and had the hydrogen on the left, this is still a fast reaction. This is not, or part of the mechanism. This is not the rate determining step. The rate determining step is when your oxygen of the ketone or aldehyde forms the four-membered ring with your phosphorus. That's when because that's really difficult to do, right? Why does it want to form this four-membered ring? That's the rate determining step. So understand that it's so much easier to make that four-membered ring, given this mechanistic setup, if your groups have less steric hindrance. So if you'll notice, this phosphorus with my ester on it, that ester is coming out at us, while the groups that were on my aldehyde, the R group and the ester, are opposite. They're trans to one another. One's in the front, the ester is in the front in blue, and the R group is in the back. And this is the best way to form the four-membered ring. And that's why we can do this rate determining step much faster if I form a trans double bond, if I'm on my way to forming a trans double bond, than if I were trying to form the cis double bond. This would be a much slower reaction. Hence the double bond, once this collapses, this is a fast part of the reaction. When that collapses, the double bond formed is going to be preferentially trans, or E.